in this case, we have this as the source code. So the scanner will just generate the tokens, and all the tokens are valid because we're able to associate the tokens with the lexings. But then this parser generates an error because it's not able to associate the token stream with a structure from the grammar for this language. So really that's what the parser is supposed to do. Receive the input from the scanner, check whether that input is generated by the grammar by ensuring that you can come up with a parse tree. If yes, accept. If not, generate an error, a syntax error. Okay. So what is syntax analysis? So after scanning, which is the lexical analysis, we generate a series of tokens. And the role of syntax analysis is to interpret what those tokens mean. And by saying we're interpreting, basically there are two goals here. The first one is to identify the structure that is described by the series of tokens. And here, of course, the structure is asking, are we able to generate from the start symbol of that CFG, draw a parse tree or come up with a parse tree of which tokens and which non-terminals and terminal symbols have been used up to when we get the leaves at the bottom of the tree. So we have a complete parse tree. And that means we have recovered the structure that has been used for the token stream. Else, if that doesn't work, then generate an error. So this will be your next task. Once you're not done with the scanner, the next thing is to build the syntax analysis. So you need to start now really listening to what the task of syntax analysis looks like, what are the goals, and you start figuring out how you then interface from your scanner to now process the tokens as they come in. So thoroughly we have that. So we have the parser in the middle here, the two inputs that it uses, of course. The first one is the context-free grammar. You've already come up with a mini grammar that you're using for your project. So there it defines all your non-terminals and terminal symbols and the rules that derive a particular non-terminal to a terminal symbol. So that is the reference that the syntax analyzer has. And then it receives the token stream from the lexicon, and its work is to just determine if S is in the language of the grammar. In other words, can we uncover the structure starting from the start symbol of that grammar to the token stream that we have gotten from the lexa? If yes, we accept. If no, we generate appropriate error messages. So syntax analyzers are CFG acceptors. And I think you remember what a CFG is, although we're going to quickly go through that. So they accept a CFG and use that CFG to determine whether the token stream from the scanner is actually forming a valid sentence or valid string in the grammar of that CFG. If at all, we can get a derivation from the tree. So in terms of understanding the syntax analysis phase, we're going to go through the formalisms for syntax analysis, the same way we did for scanning. We talked about regular languages. We refreshed our minds on regular expressions, deterministic FAs, NFAs, and converting NFAs and all that. So that was the bit that comes for lexical analysis. So we're going to do the same thing. What are the formalisms for syntax? So CFGs, derivations, the notion of concrete versus abstract syntax trees, and the biggest problem for a syntax analyzer, which is ambiguity. And then we're going to look at the different types of algorithms that are amenable to us to build our syntax analyzers. So we have top-down parsing, we have bottom-up parsing. So we start with the formalisms. So this is just a refresher. We already know when we are talking about scanning, the alphabet is basically a set of symbols that act as letters. And a language of a certain alphabet is basically the set of strings that can be formed by combining symbol from signal. So when we're building our scanner, basically we're using either ASCII as our alphabet or Unicode characters. And then we have rules that show us, and these are regular expressions that show us how we combine the alphabet into valid tokens, or rather into like symbols that we associate with the tokens. So when we're parsing, now we can think of the alphabet, which is what the unit from which we form the units that we are trying to make sense of. In this case, we think of the token stream as the alphabet for the parser. So it only recognizes tokens and tries to figure out the structure. So we already know the limits of regular languages. And I remember what we did in the year 2 course on automata theory. We said that regular languages, or rather we have regular expressions, DFAs and FAs, used to describe regular languages, but we say there's a class of languages that cannot be expressed using regular expressions because they are not regular. And if you remember, it was because regular languages, or even the tools that we're using, like DFAs, etc., do not have a capacity to count. So there are many things that cannot be expressed using regular expressions. Okay. So, for example, if we're trying to build to confirm that parentheses are matching, that there's a left for every left parenthesis, there's a matching right parenthesis, you can't do that using regular expressions. Okay? And even if you're trying to check nested block structures, you cannot do that with regular expressions, because now that is more than a regular language. So these are context-free languages. And that's why we said we needed a now more powerful formalism to represent those class of languages that are not regular. Okay? And this is why now we introduced CFGs. So I hope you all remember that. So this is stuff we already know, so I'll move pretty fast. So a CFG is basically a formalism for defining context-free languages. And this is a superset of regular languages. So CFGs can define both regular and context-free languages, but not the other way around. The formalism for regular languages cannot be used to define context-free languages. So just to refresh our minds, so this is an example of a CFG. So if we take the language of arithmetic expressions, suppose we want to describe all the legal expressions that we can have, that is addition, subtraction, multiplication, and division for now. There are many ways to express that CFG, and this is one example. So you could have our non-terminals here. We could say that expression is written as int. So in this case, whatever is in blue and small case is a terminal symbol. Whatever is in red and uppercase is a non-terminal symbol. Then the other option for expression is that an expression can be written as an expression, an operator, an expression, or an expression in brackets. Operators, we have 4 different types. Operator can be written as a plus, as a minus, as a times, as a division. And then now what we do is that once we have the CFG, we're basically trying, once we get our input, our token stream, which would be coming now from the scanner. So scanner in this case is saying there's an int, token times, token left parent, token int, token plus, token int, etc. The role of the parser now is to try and figure out which sequence of production rules from this CFG generate this string. Okay. So in this case, we'd say, here's plus, op can be written as plus. So we now have int times int of int, and then we write this int. This expression is written as int. We're disconnected. Oh, shit. Things of division.